Okay, so we've got things set up, but how are series actually going to help us out when it comes to solving an ordinary differential equation? Let's keep things simple. Let's go back, think about the simplest ODE we can work with, our old friend, the linear ODE. You remember that guy, right? Right, we like this one. This is really nice. We've got dx dt equals lambda times x, where lambda is a constant. Now let's expand, as we did before, assuming that x of t is the sum, k goes from 0 to infinity, of c sub k, t to the k. With these constants, c sub k, they're unknown. We got to figure them out. If we have that, then the derivative, dx dt, is the sum k goes from 1 to infinity of k times ck times t to the k minus 1. Now we're going to substitute these into the differential equation. On the left-hand side, what do we have? The sum k goes from 1 to infinity of k ck t to the k minus 1. That's dx dt. On the right, we have lambda times x, where x is the sum k goes from 0 to infinity c sub k t to the k. And there we go. That's it. Has this helped us? What are we going to do? Well, we have two series that are equal to one another. And remember our principle that says that happens if and only if the coefficients match up. However, what we have is not quite in that form. I've got powers of t on either side that don't quite match up. So let's make these two series compatible. Let's change the left index to make things fit. The way we're going to do that is we're going to define a new index, L, that is k minus 1. Or if you like, you could substitute in L plus 1 for k. Doing so gives us on the left the sum L goes from 0 to infinity. I like that. What's inside? K becomes L plus 1, c sub k becomes cl plus 1, and t to the k minus 1 becomes t to the l. On the right, I'm going to repeat the same thing, but instead of using k, I'm just going to switch it to a new index. I think I'll use the letter L. So on the right, we have lambda times the sum L goes from 0 to infinity, cl t to the l. And now this is good. This is in the form that we had from our previous principle, where now we can match things up. So let's do that. Let's move that lambda to the inside on the right. And I have these two sums that are equal to one another. They have the same powers of t matching up. The summation limits both go from 0 to infinity. Everything's fine. What we can say is that the coefficients must be the same. That is, quantity L plus 1 times CL plus 1 must equal lambda times C sub L. This has to hold for all values of L based on that previous principle we talked about. Now, what's nice about this is these are algebraic equations, and we can solve them inductively. What does that mean? If I move things around a little bit, I get the equation C sub L plus 1 equals lambda divided by L plus 1 times CL. This is something called a recurrence relation. But whatever, let's just start working with it. We've got our first coefficient C0 when L equals 0. From that, I can figure out C1 equals lambda divided by 0 plus 1 times C0. So if I know C0, I know C1. What's C2? Well, by that formula, C2 equals lambda divided by 1 plus 1, that's 2, times C1. But I know what C1 is, so I get that C2 is lambda squared over 2 times C0. Let's keep going. What's C3? I'm going to plug in L equals 2 into that formula. I get that C3 is lambda divided by 3 times C2, which is lambda cubed over 6 times C0. Now step back, take a look. Aha, I see a pattern. Inducting, you can show that C sub n, for general n, is lambda to the n divided by n factorial times C0. And if we go back, we think that x is the sum n goes from 0 to infinity of Cn t to the n. I can use whatever letter I want for the index. Then we can substitute this in and get the sum n goes from 0 to infinity of lambda to the n divided by n factorial times c naught times t to the n. And now we're almost done here, because if we go back to when we started working on this problem and we have x of t in terms of this series, we now know what the coefficients are if I factor out the c naught that appears in every term. Then what's left over is the sum n goes from 0 to infinity of 1 over n factorial times, what I can do is take the lambda and the t, put them together, raise that to the nth power. And now I see our old friend, the exponential function, written out in that series. This is, of course, c naught times e to the lambda t. And voila! That is, of course, the solution to the linear ordinary differential equation. It's really interesting that we solved for this. We got this solution without doing any integration, or so it would seem. We're merely manipulating series according to the principle that we had, that two series are the same if and only if all their coefficients match. That winds up converting this ordinary differential equation into a set of algebraic equations, which we solved inductively.